The ratio of areas within an electron orbit for the first excited state to the ground state for hydrogen atom is, we know that R is directly proportional to n square. So area of nth orbit is directly proportional to n raised to 4. Therefore A1 upon A0 is equal to 2 upon 1 raised to 4, which is equal to 16 is to 1. So option A is the correct answer. The ground state of energy of hydrogen atom is minus 13.6 eV. What is the potential energy of electron in this state? So we have to find the potential energy, which is equal to twice of total energy. So 2 into minus 13.6, which is equal to 27 minus 27.2 eV. So potential energy is minus 27.2 eV. The ionization energy of lithium ion is equal to, we know that ionization energy is equal to RCHZ square, where Z is the atomic number. Substituting Z is equal to 3 as it is lithium ion, we get RCH into 3 square. So we can write this as 9 RCH. So option A is the correct answer. Protons are kept at a separation of 40 angstrom. Fn is the nuclear force and Fe is the electrostatic force between them. Then we have to compare Fn and Fe. The nuclear force is much strongest than the electronic force inside the nucleus. So nuclear force is much strongest than electronic force. That is distance of the order of Fermi. At 40 angstrom, nuclear force is ineffective and only electrostatic force of repulsion is present. This is very high at this distance because nuclear force is not acting now and gravitational force is very feeble. So only electrostatic force is acting because of the distance is large. Nuclear force is more effective when there is distance is in Fermi units. So for now, force of nucleus will be very less than electrostatic force in this case. So option A is the correct answer. Hydrogen atom is excited from ground state to another state with the principal quantum number is equal to 4. Then the number of spectral lines in the emission spectra will be. So we have to find the number of spectral lines from quantum number n is equal to 4. Number of lines will be n into n minus 1 upon 2, which is equal to 6. So option D is the correct answer. Beta decay means emission of electron from A innermost electron orbit, B a stable nucleus, C outermost electron orbit, D radioactive nucleus. In beta decay, an electron is emitted by the radioactive nucleus. As in the decay example of phosphorus, which is 1532, it becomes to sulfur plus an electron is released, where this is antineutrino. In beta plus decay, this is beta minus decay, and in beta plus decay, a positron is emitted from the radioactive nucleus. So a sodium will be sodium only plus a positron, and this is neutrino. So option D is the correct answer. Beta decay emission occurs from radioactive nucleus. Mass of lithium nucleus is 0.042 atomic mass unit, which is less than the sum of the mass of its nucleons. The binding energy per nucleon of lithium nucleus is nearly. We have to find the binding energy divided by per nucleon, which is equal to 0.042 into 931 upon 7. On solving this, we get 5.6 mega electron volt. So option C is the correct answer. 1 milligram of matter converted into energy will give. We know that energy is equal to mc square. So mass is 10 raised to minus 6 into c square is speed of light, 3 into 10 raised to 8 the whole square. On solving this, we get 9 into 10 raised to 10 joules in SI unit. So option C is the correct answer. The rest energy of an electron is. The rest energy of electron, we can write it as mc square, where mass of electron is equal to 9.1 into 10 raised to minus 31 kg and c is the speed of light. Therefore, rest energy is equal to 9.1 into 10 raised to minus 31 into 3 into 10 raised to 8 the whole square per electron, which is the charge 1.6 into 10 raised to minus 19. This is important. We have to convert this in EV. Therefore, resting energy on solving, we get 510 kilo electron volt. Option A is the correct answer. What is the particle X in the following nuclear reaction is? When beryllium plus helium will give carbon plus X. So in the following reaction, beryllium has mass 9, helium has mass 4, the total is mass 13. So here atomic number is 6 and the total is 6. So there is no change in the number of protons or neutrons, but here the number is different in atomic mass. So X will be 0, 1. So this is a neutron. Option D is the correct answer. Nuclear ruptures into two nuclear parts which have their velocity ratio equal to 2:1. What will be the ratio of their nuclear size or nuclear radius? So as the momentum is conserved, so mass m1 which is given, so the mass m1 upon m2 is equal to a1 upon a2 equal to v2 upon v1, which is equal to half. Therefore, R1 upon R2 is equal to A1 upon A2 raised to 1 by 3. So, half raised to 1 by 3 is the correct answer. So, option B is the correct answer. A gamma ray photon creates an electron positron pair. If the rest mass of energy of an electron is 0.5 milliequivalent and the total energy of the electron and positron pair is 0.78 MeV, then the energy of the gamma ray must be. So energy of gamma ray photon is sum of all the energy given, 0.5 plus 0.5 plus 0.78, which is equal to 1.78 mega electron volt. This is energy of gamma photon. Option B is the correct answer. 1 gram of hydrogen is converted into 0.9339 of helium in a thermonuclear reaction. The energy released is. So we know that the mass is equal to 1 minus 0.993 approximately. So on we are remained with 0.007 gram of mass. Therefore, energy is equal to delta m change in mass c square. So 0.007 into c square is speed of light the whole square. So we get 63 into 10 raised to 10 joules on solving. So option B is the correct answer. If a proton and an antiproton come close to each other and annihilate, how much energy will be released? So mass of proton is equal to mass of antiproton, which is equal to 1.6 into 10 raised to minus 27 kilogram, which is equal to 1 AMU. Energy equivalent to 1 AMU is equal to 931 mega electron volt. So energy equivalent to 2 AMU is equal to 2 into 931, which is equal to 1862 into 10 raised to 6 into 1.6 into 10 raised to minus 19. On solving this, we get 2.97 into 10 raised to minus 10 joules, which is approximately equal to 3 into 10 raised to minus 10 joules. So option B is the correct answer. If the energy released in the fusion of one nucleus of nuclei required for second in a power plant is 16 kilovolt will be. So energy released in a fission of one nucleus is equal to 200 mega electron volt. So we can write this as 200 into 10 raised to 6 into 1.6 into 10 raised to minus 19 joules. So converting the energy in joules, 3.2 into 10 raised to minus 11 joules. So power is 16 kilovolt is given, which is 16 into 10 raised to 3 watt. Now number of nuclei required per second is equal to power upon E, energy. 16 into 10 raised to 3 divided by 3.2 into 10 raised to minus 11. On solving, we get 5 into 10 raised to 14. So option D is the correct answer. In the nuclear reaction, X N1 alpha thrice lithium of mass 7. In the term, X will be. So here X, where N alpha lithium of atomic number 3 and mass 7 will give an element plus a neutron in a nuclear reaction. So further we get lithium 7 and number 3 plus helium 4 and mass 2. Therefore Z is equal to 3 plus 2 is equal to 5 and A is equal to 7 plus 4 minus 1, which is equal to 10 minus 1, which is equal to 10. So from here we can write X is equal to 10, 5, which is equal to B, 5, 10, option A. The nuclear reaction hydrogen plus hydrogen of mass 1 will give helium. The mass of deuteron is this and the mass of helium is this. Option A, fusion reaction releasing 24 mega electron volt of energy. Fusion reaction absorbing 24 mega electron volt. Fission reaction releasing this much energy. Fission reaction absorbing this much energy. So we have to find the total mass of the reactant. Total mass of reactant is equal to 2.0141 into 2. So we get the total mass of the reactant is 4.0282 AMU. Total mass of product is equal to 4.0024 AMU. So the mass defect is equal to 4.0282 AMU minus 4.0024 AMU. So on solving, we get 0.0258 AMU. So we have to find now energy released, which is equal to 931 into 0.0258. So on solving this, we get 24 mega electron volt energy is released on a fusion reaction. The energy in mega electron volt released due to transformation of 1 kg mass completely into energy is where speed of light is given. So energy can be written as delta m c square. The mass is 1 kg and c is 3 into 10 raised to 8 the whole square. We get 9 into 10 raised to 16 joules. Converting this energy into electron volt, we get 9 into 10 raised to 16 divided by 1.6 into 10 raised to minus 19. On solving, we get 5.625 into 10 raised to 35 electron volt of energy. Converting this into mega electron volt, we get 5625 into 10 raised to 29 electron volt. Option D is the correct answer. Using the following data, mass of hydrogen atom is this and the mass of neutron is this, mass of nitrogen atom is this. The calculate value of binding energy of the nucleus of nitrogen atom is close to. So we have to find the binding energy for nitrogen atom. So it will be 7 into 1.00783 plus 7 into 1.00867 minus 14.00307. This is the mass of the nitrogen atom, first mass of the hydrogen and the mass of the nitrogen atom, neutron. So on solving this, we get binding energy is equal to 0.11243 into 931.5. So this is the change in mass, and now we have to find the energy, 104.7 mega electron volt. So option C is the correct answer. If the nuclear radius of aluminum is 3.6 Fermi, the approximate nuclear radius of copper in Fermi is of mass 64. So we know that radius is equal to R0 a raised to 1 by 3. So R2 upon R1 is equal to A2 upon A1 with raised to 1 by 3 is equal to 64 is the mass and 27 1 by 3. On solving this, we get 4 by 3. So R2 is equal to 3.6 into 4 by 3. 3.6 is R1, so 4.8 is the radius R2 of copper. Option C. If the radioactive substance at T0, the number of atoms is this much. Its half-life period is 3 years. The number of atoms this much will remain after interval is. So by formula, n is equal to n0 into half raised to 1 by t, time period, t by t, small t by capital T. Or we can write this as 10 raised to 4, substituting the values, 8 into 10 raised to 4, 1 by 2 raised to t by capital 3 is the half-life period. Or we can write further this as 1 by 8, which is equal to half raised to small t by 3. We can write 1 by 8 as 1 by 2, 1 by 3 is equal to, this is raised to 3 and half raised to t by 3. So comparing, we can write 3 is equal to t by 3. Therefore, time is equal to 9 years. So option A is the correct answer. The half-life period of radium is 1600 years. The fraction of sample of radium that could remain after 6400 years is, fraction is equal to n upon n0, when n0 is the initial fraction mass. We can equate this as half into small t by capital T, which is 6400 upon 1600. 1600 is the half-life, which is capital T. So we can write this as n upon n0 is equal to half raised to 4. So n upon n0, the fraction is equal to 1 upon 16. Option D. What percentage of original radioactive atom is left after half-life? So the fraction of atoms left after 5 half-life is n upon n0 is equal to half small t upon capital T, which is equal to half phi t upon capital T, which is equal to 1 upon 32. Percentage of atom remain 1 upon 32 into 100, which is equal to 3.125%. Option D. A nucleus of atomic mass A and atomic number Z emits beta particle. The number of atomic mass of the resulting nucleus is. So we have to find the Z and the atomic mass. So X is the element, Z and A. One beta elimination occurs. So it will lead to XA. There will be no change in the atomic mass and the atomic number will be Z plus 1 as the negative charge is removed. So option C is the correct answer. The ratio of half-life times of two elements A and B is Ta upon Tb. The ratio of respective decay constant is. So T half is equal to ln 2 upon lambda. Therefore, lambda is equal to ln2, which is natural logarithm of log 2 upon T half. So lambda A is equal to ln 2 upon half-life of A. Lambda B is equal to natural logarithm of 2 upon time B. So lambda A upon lambda B is equal to time B upon time A. Option A is the correct answer. If T is the half-life of the radioactive material, then the fraction that would remain after time T by 2 is. Fraction remain by n half-life can be written as n upon n0 is equal to half raised to n. Half raised to small t by capital T is the natural formula. So n upon n0 is equal to half raised to time t by 2 divided by original half-life. We can write this as half raised to half, which is 1 upon root 2. Option C is the correct answer. Which of the following is the increasing order of the penetrating power, alpha, beta or gamma? So the percentage of penetrating power of gamma is 100 times of beta, while that of beta is 100 times of alpha. So the increasing order will be alpha to beta to gamma. Gamma is the highest penetrating power. The decay constant of radium is this much per year its half-life will be. So we can write T is equal to 0.693 into 1 upon lambda. So 0.693 upon lambda is 4.28 into 10 raised to minus 4 years. On solving this, we get 1620 years. Option D is the correct answer. A sample contains 16 grams of radioactive material, the half-life of which is 2 days. After 32 days, the amount of radioactive material left in the sample is A. Less than 1 milligram, B. Half into 9, B. 1/4 of 9 and D. 19. So the remaining amount we have to find out, which we can find as a sample contains 16 gram of atoms. So remaining amount is equal to 16 into a half into 32 by 2 after 32 days. So 16 into half raised to 16. So on solving this, we get half raised to 12, which is less than 1 milligram. Option A is the correct answer. 3 alpha particle and 1 beta particle decaying takes place in series from an isotope of radium of mass 88, 236 and atomic number 88. Final isotope obtained is. So using n alpha is equal to A minus A dash upon 4 n beta is equal to 2 n alpha minus z plus z dash. Therefore, a dash is equal to a minus 4n alpha, which we can write as 236 minus 4 into 3, which is equal to 224, and z dash is equal to n beta minus 2n alpha plus z, which we can write as 1 minus 2 into 3 plus 88, which is equal to 83. So x 224 83. Option C is the correct answer. Two nuclei have their mass number in the ratio 1:3. The ratio of their density is, so nuclear density is independent of the mass number, as the required ratio will be 1:1. It is independent of the mass. So option B is the correct answer. Nuclear fusion reaction is given when two hydrogen fuse to form a hydrogen with mass 3 and number 2 plus 1 neutron is released plus energy. The 2 moles of deuterium are fused, then the total energy released is, so we have to find the total energy released, that is Q into Avogadro number, which is equal to Q into 6 into 10 raised to 23. Option C is the correct answer. If the half-life of a radioactive sample is 10 hours, its mean life is, so mean life is equal to half-life upon 0.6931, which is equal to 10 upon 0.6931, which is 14.4 hours. So option A is the correct answer.